Good morning. It is good to see you all here. I see we have a full house today. That is wonderful because we have a very interesting problem to talk about. It is a problem that has bothered people for a long time, and honestly, it still bothers me quite a bit when I try to sleep at night. We are going to talk about gravity, but not the boring kind you learn in high school. We are going to talk about what happens when gravity goes crazy. We are going to talk about holes in the sky. Now look at this. I have a piece of chalk in my hand. If I let go of it, what happens? It goes down. It hits the floor. You say, well, of course it does, Professor. Gravity pulled it. And if I ask you what gravity is, you might say it is a force. You might imagine a little invisible rope tied to the chalk, pulling it toward the center of the earth. That is what Isaac Newton thought. He was a very smart man, Newton. He gave us rules that work beautifully for building bridges and firing cannons and even for keeping the moon in orbit. For a long time we thought that was the end of the story. Objects pull on each other. Simple. But then along came Albert Einstein and he upset the whole apple cart. He said, no, that is not it at all. He said there is no invisible rope. He said the chalk does not feel a force. He said the chalk is just trying to follow a straight line. But the world it lives in, space itself, is curved. Now that sounds like philosophy, doesn't it? It sounds like something you say at a cocktail party to sound deep. But it is real, it is physical. I want you to imagine something concrete. Forget the fancy mathematics for a moment. Imagine we take a nice clean bed sheet and we stretch it out tight between 4 people, one at each corner. It is flat. If I roll a marble across it, the marble goes in a straight line. Easy. Now suppose I take a heavy bowling ball and I place it right in the center of that sheet. What happens? The sheet sags. It curves down in the middle. Now if I roll that same marble across the sheet, what does it do? It does not go straight anymore. It curves, it bends toward the bowling ball. Did the bowling ball reach out and grab the marble? Did it tie a rope to it? No. The bowling ball just changed the shape of the sheet, and the marble had to follow that shape. That is what Einstein meant. Matter, the earth, the sun, you, me, we tell space how to curve, and space tells matter how to move. The chalk falls because the earth has made a valley in space, and the chalk is just rolling down the hill. So far so good. This works for the earth. It works for the sun. But we physicists, we are never satisfied with the ordinary. We like to push things until they break. We want to know what happens if you take that bowling ball and make it heavier, and heavier, and heavier. Or even more interesting, what if we keep the weight the same but squeeze it down? Let's talk about escaping. It is a very important idea. Suppose I want to leave this room. I can just walk out the door. But suppose I want to leave the earth. That is much harder. If I take this chalk and throw it up, it slows down and comes back. Gravity wins. If I had a better arm, like a baseball pitcher, I could throw it high, but it still comes back. To get away and never come back, I need speed. I need a lot of speed. We call this escape velocity. For the earth you need to be moving at about 25,000 miles per hour to break free. That is fast. That is why the boys down at Cape Canaveral need those gigantic rockets. They are fighting to reach that speed. If they go 24,000 miles per hour, they fall back. If they hit 25,000, they are gone. They are free. Now here is a game we can play. The escape velocity depends on 2 things: how heavy the planet is and how small it is. If I could use a magic pump to squeeze the earth down until it was half its size, the gravity on the surface would get 4 times stronger. It would be much harder to escape. I would need to throw my rock fast. If I kept squeezing the earth, crushing all the rocks, the water, the buildings, everything until it was the size of a peanut, the gravity right next to it would be unimaginable. To escape from that peanut-sized earth, you would need to move incredibly fast. And this brings us to the ultimate speed limit. You see, in our universe, there is a law. It is not like a traffic law where you get a ticket if you break it. It is a law you cannot break. Nothing goes faster than light. Light travels at Mundity 6,000 miles per second. That is it. That is the top speed. There is no gear higher than that. So here is the question that should make you scratch your head. What happens if we have a star that is so heavy and squeezed so small that the escape velocity is faster than the speed of light? Think about that. To get out you would need to go faster than light. But nature says no, you cannot do that. So if light cannot get out and nothing is faster than light, then nothing can get out. Nothing. Not a rocket, not a radio signal, not a reflection. If you shined a flashlight up from the surface of such a star, the beam would just curve back down and hit the ground like a tossed rock. From the outside, what would we see? We wouldn't. It would be black. A perfect, absolute blackness. A hole in the universe where things go in and nothing comes out. For a long time we thought this was a joke. We thought it was just math doodling. We called them frozen stars or dark stars. It seemed too ridiculous to be real. Nature is usually more sensible than that. But nature, it turns out, does not care what we think is sensible. In the last few decades we have looked up at the sky with our radio telescopes and our X-ray detectors, and we have found them. They are out there. We call them black holes now. But I want to take you closer. I want to talk about what it is like to get near one of these things. This is where it gets really interesting, and where our common sense starts to fail us completely. Imagine we are in a spaceship. We are floating in space, far away from a black hole. It looks like a circle of nothing, like someone cut a hole in the starry background. As we get closer, we feel the pull. It is gentle at first, but there is a specific boundary we are looking for, a point of no return. We call this the event horizon. I like to think of it like a river. Imagine you are in a canoe on a wide, lazy river. The water is flowing toward a waterfall, a really big, dangerous waterfall. But you are far upstream. The water is moving slowly. You can paddle your canoe faster than the water flows. If you want to turn around and go home, you can. You just paddle upstream. But as you get closer to the edge, the river narrows. The water speeds up. Now the current is moving at 5 miles an hour. If you can paddle at 6 miles an hour, you are still okay. You can make progress, but you have to work harder. Closer still. The water is rushing now. It is moving at 10 miles an hour. If you paddle with everything you have, maybe you can match it. You can stay in one spot, sweating, paddling furiously just to keep from going over. The event horizon is the line in the river where the water is flowing at exactly the speed you can paddle. In space, the water is space itself, falling into the hole, and your paddling speed is the speed of light. At the event horizon, space is falling into the black hole at the speed of light. Since you cannot go faster than light, you cannot paddle upstream. You are stuck. If you are exactly on the line, you could shine a flashlight away from the hole, and the light would just stay there, frozen, unable to move forward, unable to fall back. It is trapped. If you cross that line even by an inch, the space around you is moving toward the center faster than light. No matter what you do, no matter how big your rocket engine is, you are going down. There is no out anymore. The future only points in one direction, inward. This is a very strange concept. Usually we can choose where to go. We can go left, right, up, down. But inside the horizon, out, is not a direction anymore. It is like trying to go to yesterday. You cannot go to yesterday. Time only marches forward. Inside a black hole, the center is not just a place. It is a time. It is your future. You are going to hit it, just as surely as you are going to hit next Tuesday. Now you might ask, okay, Professor, so I fall in, what happens to me? Well, I have some bad news. It is not going to be a pleasant trip. The problem is the tides. You know about tides on Earth. The moon pulls on the oceans, but really the moon pulls on the whole Earth. It just pulls on the side facing it a little harder than the side facing away. That difference stretches the water out. Near a black hole, gravity is intense, but it is not just strong, it changes very fast. Suppose you are falling feet first. Your feet are closer to the center than your head. If the black hole is small enough, the pull on your feet is much, much stronger than the pull on your head. You would feel a stretch, a terrible stretch. It would feel like you were being pulled apart on a medieval rack. At the same time, because everything is trying to squeeze into the center, you would be crushed from the sides. You would be stretched out long and thin, like a piece of spaghetti. It is a violent, destructive process. The technical term, and I am not making this up, is spaghettification. It happens to stars, it happens to gas clouds, and it would certainly happen to you. But let's assume, for the sake of our little thought experiment, that you are very tough. Or maybe the black hole is very big, so the tides are gentle at first. You survive the crossing of the horizon. You are alive. You are inside. You look around, you can see light coming in from the universe outside. It looks like a bright circle above you, shrinking as you fall. But you cannot send a postcard home. Nothing you do leaves this bubble. you are cut off from the rest of reality. We need to pause here and think about the tools we use to describe this. When I draw diagrams on the board, or when you see those equations in textbooks, with all the little curly symbols, what are we actually doing? We are using calculus. Now don't panic. Calculus is just a fancy word for the study of how things change. When things stay the same, math is easy. If a car goes 50 miles an hour forever, you don't need calculus. But things in the real world don't stay the same. They speed up, they slow down, they curve. When you fall into a black hole, everything is changing. The gravity is getting stronger every split second. The space is curving more and more sharply. We need a way to track that change. We need to be able to look at what is happening at this exact instant, and then the next instant, and the next. That is what those little symbols, derivatives and integrals do for us. They are like a microscope for time and space. They let us zoom in on a tiny slice of the journey. We say, okay, right now, the curvature is this much. A millisecond later it is this much. We stitch those tiny slices together to make a movie of your fall. And when we run that movie, when we follow the equations of general relativity all the way down, they tell us something terrifying. They predict a crash. Not a crash like a car hitting a wall. A crash of the theory itself. As you fall deeper, the density of stuff gets higher. The curvature of space gets tighter. The numbers in our equations get bigger. They go to 1,000, then 1,000,000, then 1,000,000,000. And then at the very center, the equations cough up a result that no physicist ever wants to see. They give us infinity. They say that all the matter of the star, all that mass, all that energy, is crushed down into a point with zero size, infinite density, infinite curvature. We call this the singularity. Now you have to understand something about physicists. We are practical people. We measure things. We measure 5 pounds, 10 meters, 12 seconds. We never measure infinity. Infinity is not a physical number. It is a mathematical concept. It is what you get when you divide by zero. If you have a mechanical calculator, you know, the old crank kind, and you try to divide by zero, the gears jam, the machine stops, it might even break. The singularity is nature's way of telling us that our calculator is broken. It means our theory of gravity, as beautiful as it is, has failed. It works perfectly out here. It works perfectly near the horizon. But right at the center it gives us nonsense. This is the great mystery. We know there is something there. The matter didn't just disappear, but we cannot describe it. It is wrapped in a cloak of mystery, hidden behind the horizon. It is a place where space and time as we know them cease to exist. So here we are. We have taken a nice walk. We started with a piece of chalk. We threw it at the stars. We found a hole in the sky. We paddled over the waterfall, and now we are falling into the dark, rushing toward a point where the laws of physics seem to divide by zero. It is a bit scary, yes, but it is also wonderful, because it means there is something left to discover. It means the story isn't over. We have the clues. We have the equations. We just need to be clever enough to figure out what happens when the gears jam. In the next part of our discussion, we are going to try to do just that. We are going to look at what happens when the very big world of gravity crashes into the very small world of atoms. We are going to see if we can find a way to fix the calculator. We are going to peer into the heart of the monster. But for now, just think about that chalk. Think about the invisible curves in the room, and think about how fragile our understanding of down really is. Because down there in the dark, down goes on forever. So we are falling. We have crossed the line, paddled over the waterfall, and now we are rushing toward the center. We talked about the stretching, the spaghetti problem, and that is bad enough. But now we have to face the real monster, the thing waiting at the bottom. We call it the singularity. It sounds like a fancy club downtown, but it is actually the most frustrating spot in the entire universe. And to understand why it makes us pull our hair out, we have to talk about measuring things. In physics, we like to measure. We like to say, the temperature is 72 degrees, or the mass is 5 kilograms. We like specific numbers. But what does the theory of gravity tell us about the center of a black hole? It tells us the density is infinite. It tells us the curvature of space is infinite. Now you have to be careful with that word, infinity. It is easy to say. You can write it down a little figure 8 on its side. But in the real world, what does it mean? If I told you I had infinite chalk in my pocket, you would know I was lying. My pocket has a bottom.
The room has a ceiling. There isn't enough room in the universe for infinite anything. When a physicist sees infinity pop out of an equation, we don't cheer, we panic. It is nature's way of slapping our hand. It is an error message. It means our calculator has jammed. Imagine you are doing long division on paper. You are dividing 1,000 by 2. You get 500. Divide by 10. You get 100. But if you try to divide by 0, what happens? You can't do it. The rules of arithmetic stop working. That is what the singularity is. It is the point where the rules of space and time divide by 0. According to Einstein, all that stuff, the dead star, the gas, the light, the unlucky astronauts, everything gets crushed down into a point smaller than an atom, smaller than a proton, smaller than anything. 0 volume. But it still has all the mass. That means the density is limitless. This bothers us. It bothers us a lot, because we know that things in nature don't just vanish into mathematical points. Something else must be happening. The theory of gravity, general relativity, is a beautiful theory. It describes the curves and the smooth shapes of the universe perfectly. But it is a classical theory. That means it assumes space is smooth. Like a sheet of rubber. You can zoom in, and it is still smooth. But we have another rulebook in physics, a completely different rulebook for the tiny world, the world of atoms and electrons. It is called quantum mechanics. And let me tell you, these two rulebooks do not get along. They are like two neighbors who hate each other. General relativity says, space is smooth and predictable. I can tell you exactly where the planet is. Quantum mechanics says, no, space is messy. Particles are jittery. You can never know exactly where anything is. Usually they stay in their own backyards. Gravity rules the big stuff. Stars, galaxies. Quantum mechanics rules the tiny stuff. Atoms, photons. They almost never meet. The gravity of an atom is so weak we can ignore it. And the quantum jitter of a planet is so small we can't see it. So we use one book for the big stuff, and the other book for the small stuff. And everyone is happy. But inside a black hole, we have a disaster. We have a star, which is huge and heavy. So we need gravity crushed down to the size of a speck. So we need quantum mechanics. We are forcing the two neighbors to live in the same tiny apartment, and they start throwing plates at each other. Let's look at this through the lens of the uncertainty principle. This is a famous idea from Werner Heisenberg, back in the old days. It says you cannot pin a particle down perfectly. If you try to squeeze an electron into a tiny box, it starts moving faster. It goes crazy. It buzzes around because you have trapped it. The tighter you squeeze it, the faster it moves. It refuses to sit still. It demands a certain amount of elbow room. So now think about our singularity. Gravity is trying to crush everything to a 0 point. It wants to squeeze the star into literally no space at all. But quantum mechanics screams, you can't do that. The particles, or whatever is left of them, should be buzzing with infinite energy to fight that squeeze. Gravity says, 0 size. Quantum says, you need space. Who wins? We don't know. That is the honest truth. We are missing the instruction manual for this specific part of the machine. We are looking for a new theory that combines them. A theory of quantum gravity. We have some bright ideas. Lots of chalk dust has been made over it, but nobody has cracked the safe yet. But even without that final answer, we can still figure out some amazing things if we are clever. And this brings me to one of the most shocking surprises we found in the last few years. It turns out that black holes might not be truly black. Now stick with me, because this is a bit weird. It involves the vacuum of space. We used to think empty space was, well, empty, nothing there. But quantum mechanics tells us that is wrong. Empty space is actually alive. It is seething with activity. It is like a quiet ocean. On the surface, it looks flat, but if you look close, there are little waves popping up and disappearing constantly. In the vacuum, particles are popping into existence and vanishing again all the time. We call them virtual particles. They come in pairs, a particle and an antiparticle. They borrow a little energy from the bank of the universe, appear for a split second, snap back together, annihilate each other, and pay the energy back. It happens so fast you can't see it. It is happening right in front of your nose right now. Pop, vanish, pop, vanish. Usually this doesn't matter, but imagine this is happening right on the edge of the waterfall, right at the event horizon of a black hole. A pair pops up, one is just inside the edge, the other is just outside. Gravity grabs the inside one and pulls it down. Gotcha. It falls in. But the other one, it is just outside. It hasn't crossed the line. It is stranded. Its partner is gone. It can't annihilate. It can't vanish. It has become real. It has to fly away. To you watching from a spaceship, far away, it looks like the black hole just spit out a particle. It looks like the black hole is glowing. This was a huge shock to us. We thought black holes only ate things. We didn't think they could leak. But the math says they do. They radiate. We call it Hawking radiation, named after Stephen Hawking, who did the calculation in this. Now here is the catch. Nothing comes for free in physics. There is no free lunch. To make that virtual particle real, you need energy. Where did that energy come from? It came from the black hole itself. The gravity field had to pay the bill. Energy is. Einstein taught us that E equals mc squared. If the black hole loses energy to create this radiation, it loses mass. It gets a little bit lighter. It shrinks. This is incredible if you think about it. It means black holes are not eternal. They are evaporating, like a puddle of water on a hot sidewalk. It happens very, very slowly. For a big black hole, it would take trillions and trillions of years for a star-sized one to disappear. But it is happening, and as it shrinks, it gets hotter. It radiates faster. It is a runaway process. In the very last moments of its life, a black hole would get tiny and incredibly hot, and finally, poof, it would explode with the force of 1,000,000 nuclear bombs. So the ultimate fate of all that stuff that fell in the chalk, the spaceship, the astronaut, is to be recycled. It comes back out as heat and radiation billions of years later. But this creates a new headache, a big one. We call it the information paradox. You see, in physics, we believe that history is preserved. If I burn a book, I can't read it anymore. But technically, if I could collect every molecule of ash, every photon of light from the fire, and every bit of smoke, I could use the laws of physics to run the movie backward and reconstruct the book. The information is scrambled, but it is not lost. But if a black hole evaporates, what happens to the book I threw in? It comes out as random radiation, random heat. It seems like the information is truly gone. The library has been erased. If that is true, then our basic understanding of time and physics is wrong. If information can be destroyed, we can't predict the past from the future. The whole structure of science gets shaky. So we have a war going on right now. Some physicists say the information is lost, gone forever. Others say, no, it must be hidden in the radiation somehow. Maybe it is encoded in the pattern of the heat, like a secret message. Maybe the surface of the black hole stores a record of everything that fell in, like a sticker on a suitcase. We have a fancy name for that idea, the holographic principle. It suggests that maybe the whole universe is like a hologram, where the 3D world is just a projection from a flat surface. It sounds like science fiction, but we are pushed to these wild ideas because the old ideas have hit a wall. The singularity and the horizon are forcing us to be creative, and that is the beauty of it. I started this by holding up a piece of chalk, a simple thing, but if you ask the right questions about that chalk, why does it fall? What if it fell forever? What if it fell into a place where time stops? You end up rewriting the laws of the universe. We don't have the final answer yet. If you go to the library and pick up a book on general relativity, it will tell you about the curve. If you pick up a book on quantum mechanics, it will tell you about the jitter. But there is no book yet that tells you the whole story of the singularity. That book hasn't been written. Maybe one of you will write it. We need people who can think about impossible things. We need people who aren't afraid of the error messages in the calculator, because nature is there, waiting. It has a logic. It doesn't really divide by zero. We just think it does, because we are not looking at it right. There is a gear we haven't found yet, a hidden mechanism under the hood of reality. When I look at the equations, I don't see a dead end. I see a door that is slightly ajar. We can see the light coming from underneath it, but we haven't quite figured out how to push it open. So the next time you look up at the stars, don't just see points of light. Think about the holes, the places where the fabric is torn, the places where the universe is trying to hide its secret. Think about the dark stars, and remember, the game is not over. We are just getting started. Thank you very much.